Okay, just before we start, Nathan has an announcement.
So I have a correction. So we changed our mind. Next week, it will be here, except for Thursday. Thursday afternoon will be at the Institute. So at least people that are around can at least see what the Institute looks like and meet the people there. So every day next week. So in the morning, there'll be 2 lectures, Monday and Wednesday and Friday. And Tuesday will be seminars. So Monday there'll be 2 seminars in the morning. Tuesday there'll be 2 seminars in the afternoon. Wednesday 2 seminars in the morning. Thursday 2 seminars in the afternoon. And Friday 2 seminars in the morning. So all the days will be here. But one more confusing thing is Monday, Tuesday, Wednesday will be in the other building on the ground floor. So just because it's more comfortable and for a smaller amount of people. But Friday will have to be here because that room is being used. So anyways, it's all on the program on the webpage of the stream.
Very good. So it's here we are in the last day, and Fernando is going to tell us about open and closed strings in ADS5.
Thank you. Thank you very much. So I would like to start by thanking the organizers for inviting me to both the conference and to talk here. And I also, sorry, I didn't understand or didn't get the message that the Blackboard talks were preferred. So I apologize for so mandatory, but so sorry about that. But I usually prefer Blackboard because they are easier, harder to give, but easier to prepare. But okay. Anyway, so today I will be talking, so this talk will be about a set of tools to compute the string theory amplitudes on anti-de Sitter. And this is the last talk of this workshop, or almost the first one of the next one. So the idea is that it's somewhere in between, and to use Bootstrap ideas in order to answer fundamental, to understand some fundamental aspects of string theory, in this case, computing scattering amplitudes on curved backgrounds, which is a big open problem. Now, more specifically, I will deal with the scattering of 4 massless strings. Sorry. Sorry about that. I will deal with the scattering of 4 massless strings. And in the case of closed strings, they will be gravitons on ADS 5 cross S5, and we will denote that amplitude by the ADS Virasoro-Shapiro. And in the case of open strings, we will be dealing with gluons on ADS 5 cross S3. And sometimes we just denote that by the ADS Veneziano amplitude. And please stop me at any time, ask me any questions. Although it is in the using slides, I hope that it can be a very informal discussion. So please stop me if you have any questions. So we will first start by reviewing the story in flat space, and then we will use some of these things in flat space to get some intuition for curved backgrounds. In flat space, so a scattering amplitude is basically the probability that 2 particles colliding with momenta P1 and P2 result into 2 other particles with momenta P3 and P4. They can depend on many things, these scattering amplitudes. They can depend on the parameters of your theory, here collectively denoted with the letter G. Also on the particles you are scattering, of course, their masses, polarizations, etc. And in addition, on the momenta of the particles being scattered. And for relativistic theories, they depend on these 3 combinations, which are the Mandelstam variables. And for the case of massless scattering, which is the one we will be dealing with, these S plus T plus U is equal to 0, okay? Now, for string theory, for the 4-point graviton amplitude in flat space, the parameters of the theory are the string coupling constant, GS, and the size of the string, square root of alpha prime. In addition to these 2 parameters, the amplitude depends on the momenta and the polarizations of the external gravitons. However, it turns out that supersymmetry fixes the dependence on the polarizations through a computable prefactor, and this is the object that we will focus on, okay? So it's a function of GS alpha prime, and the three Mandelstam variables, S, T, and U. We know that for string theory, the computation organizes in a genus expansion, so that if you get this quantity and expand it in powers of GS, you get tree-level, genus 1, genus 2, etc., etc. Now, in principle, in flat space, we have a worksheet theory to compute these things. This becomes extremely hard, very fast, actually. But for this talk, we will just focus about tree-level amplitudes, okay? So we are looking at these sort of amplitudes, and we will look at those also in ADS. This can be computed through a textbook computation, and if you just follow Green-Schwarz-Witten, you see that this tree-level amplitude is basically given by this integral representation over the complex plane that we will come back to. Is that okay? Beautiful. Now, it is a very nice exercise. If you haven't done this integral, you go and do this integral on the complex plane, unless you are Virasoro, then you don't need to do the integral, but if you are not, then you do, probably. And then you will get something like this, okay? And to have an explicit answer is something very cool, because once we have an explicit answer, as in flat space, we can study their properties. So in the next 10 minutes, I will list and study the properties of these amplitudes, some of which have been known for like many, many decades, and some others that have been noticed only very recently, okay? Is there any questions at this point? Beautiful. Good. So you have this expression here, okay? And many properties that we can immediately see just from this representation is, for instance, that the amplitude is crossing symmetric in the three Mandelstam variables, S, T, and U. We know that the gamma functions, they have poles at 0, -1, -2, etc. So that this amplitude has poles, and the physical interpretation is that they are due to the exchange of particles, and in my conventions, and this is the mass of the particles and spin L. And the form of the poles is a pole at alpha prime S equals an integer with some polynomial as the residue in the other variable. They also have a Regge behavior, very well-known fact, for large absolute value of S, fixed T. And then something that you can also do, which is very instructive, is that you can take this and you can do an expansion in alpha prime, or equivalently, a low energy expansion for a small ST and U. Now, if you do the small alpha prime expansion, remember that I told you that alpha prime is the size of the string, so that in the limit in which alpha prime goes to 0, we get a particle, okay? So that the first term in the small alpha prime expansion corresponds to the supergravity amplitude, and then we have a tower of corrections, and this tower of corrections is given by powers of alpha prime times a symmetric homogeneous polynomial in the variables ST and U. So here you have a polynomial of degree 1, a polynomial of degree 2, a polynomial of degree 3, and so on. Is that okay? Now, there is another property that has been appreciated only very recently, and is that if you look at the zeta values here, you have this zeta 3, zeta 5, etc. And something that we can check, we can see, is that only odd zeta values appear in the low energy expansion. This is actually very clear if you look at this representation, which is very easy to check. But this very simple fact, which is kind of trivial, is actually very deep from a mathematical perspective, okay? So in the next 10, 15 minutes, we will try to see why this is very cool from a mathematical perspective. Are there any questions before we explain that? Very nice. So let me write a formula here. So let's have a look at these zeta values. So these zeta values, I said the guys that I wouldn't use the board, and I will not, but I just want to write a couple of formulas. So these zeta values, they can be defined like this in terms of sums, but also like this, but also you can define them in terms of polylogarithms evaluated at z equals 1, okay? So instead of having this sum, you can put a z to the k so that you have this function, which is called a polylogarithm on z. And then if you evaluate this at z equals 1, you recover the formula above, okay? Now, while this series converge inside the unit disk, we know that polylogarithms can be analytically continued to the whole complex plane. And as physicists, we do that all the time. And for instance, Li1, if you plug 1 here, this is just minus log 1 minus z. And you can recursively define Ln by these iterated integrals here. Now, these functions, they can be defined over the whole complex plane with a caveat that actually they are not single-valued. And we know very well that these functions, and in particular these polylogarithms, have branch cuts generally at 0 and 1, and with branch points, with branch cuts as well, okay? Now, as physicists, we like holomorphic functions, and we don't mind to work with functions which are not single-valued. Mathematicians are a bit different, and they don't care if a function is holomorphic or not, but they want a function to be single-valued, okay? So because mathematicians don't like multi-valued functions, they have actually proven that there is a way to define a single-valued version of these polylogarithms, okay? And there is a unique map called the single-valued map that takes us from these multi-valued polylogarithms to the single-valued polylogarithms, such that this map, if you require some conditions, is a unique map. And these polylogarithms, these single-valued polylogarithms, now they are not only a function of z, they are a function of z and z bar. They are weight-preserving linear combinations of these forms, and such that these differential relations are preserved. For instance, you see here that if you take the derivative of Li n, you get 1 over z Li n minus 1. We require the same for these single-valued polylogarithms. For instance, the single-valued version of log z is log z plus log z bar. The single-valued version of Li2 is the following, and so on, okay? Now, although I have presented these for just the standard polylogarithms, these can also be generalized to multiple or harmonic polylogarithms, which usually are given by this sort of nested sums, okay? Now we can play the following game. Remember that I told you that polylogarithms evaluated at z equals 1 produce what we define as the zeta values, okay? What we can do now, we can take single-valued polylogarithms and we can evaluate them at z equals 1 and see what we get. If we do that, then this defines what we call, by definition, single-valued zeta values. I'm sorry about the name. I think it's not easy to get used to, but I didn't invent it. So, for instance, if you try to do this with zeta 2, and you try to evaluate this single-valued version of L2 at 1, you just get 0. And if you do this for zeta 3, you get 2 times zeta 3. More generally, we can see that the even zeta values are not single-valued, because if you want to do this procedure, you get 0, but the odd ones are, okay? So in this case, we see that odd zeta values are single-valued, while the even ones are not. In general, single-valued zetas are a special subset of the usual zeta values. And of course, a physicist now breaks down because we know that zeta 2 is a real number, right? It is pi squared over 6. So what I am telling you that this number is not single-valued. So what mathematicians mean by that is that if you take these single-valued functions and you evaluate them at that particular number, you cannot get zeta 2, okay? While zeta 3, zeta 5, zeta 7, you can, okay? So that the important message here is that the alpha prime expansion of the Virasoro-Shapiro amplitude contains only single-valued zetas. Okay, the even zetas they are there. The even ones are not. And although this may seem a bit trivial for the case of 4-point functions, the quite interesting property here is that if you study 5, 6, 7, 8-point functions at tree level, the same things are true, okay? And when you have zetas with more than one index, with 2, 3, 4 indices, the single-valued ones are much more rare, okay? So for instance, I will tell you something, like at weight, I think 15, there is about 1,000 zetas, and only 36 of them are single-valued, and those are the 36 ones that appear when you compute closed string amplitudes, okay? So it is something which is quite magical. Beautiful. Any questions about this? Right, so there are some comments about genus 1 as well. Yeah, so for tree level, everything is established and known. For genus 1, there are also some claims and works by Schlotterer and collaborators. Yeah. Beautiful. Any other question? So at genus 2, right. So let's say tree level. So what quantity?
No, you have zeta of an even number appearing in the low energy expansion for genus 1.
Right. So for genus 1, the statement is a bit different. Yeah. So you have to modify the statement. So this is tree level. Yeah. But there are analogous statements to genus 1. Yeah. Beautiful. So we know that in flat space, we can also consider the scattering of open strings. In this case, we know that the tree-level amplitude is given by the Veneziano amplitude, which has now also an integral representation. But notice that now the integral representation is not over the whole complex plane, but is over the segment 0 to 1. This is because this is an integral over the disk instead of an integral over the complex plane. And the result is this function here, which is known as the Euler beta function. This has a very interesting representation. And for instance, you can write it down like this. And notice something quite important, that if you look at the representation for the Veneziano amplitude, the representation for the Veneziano amplitude involves only the Virasoro-Shapiro, the Virasoro-Shapiro amplitude involves only the odd zeta functions, while the Veneziano amplitude involves both even and odd zeta values. And actually, we know already in flat space, in many different ways, that the open and closed string amplitudes, the Virasoro and Veneziano, are intimately connected, okay? So there are two connections. There are at least two relations. So first, we have the KLT relations, where you take a sphere amplitude, and then you cut it into two, and then you expect this sphere amplitude to be the product of these amplitudes. And this is the statement of the KLT relations that you can write in many different ways, but a possible way to write them is like this. So for instance, from the formulas before that I gave, you can check that the closed string amplitude is the product of two open string amplitudes with some kernel, which is a simpler function, which has sines and cosines, a periodic function, okay? Then there is another relation that is, has to do with this single-valued map. So remember that I told you that these multi-valued polylogarithms, you can find a map that takes these multi-valued polylogarithms into single-valued ones. In the same way, we can define a single-valued map such that zeta to n gives 0, and zeta to n plus 1 gives 2 zeta to n plus 1. So this is like it projects over the single value on the single-valued component, okay? Now, if you define the single-valued map like this, which takes multi-value logs to single-value logs, this takes the open string amplitude to the closed string amplitude. And indeed, you can see by expanding this exponent and acting with this map, you can indeed find precisely the exponent that led to the Virasoro-Shapiro amplitude. Okay? So this is how we usually write this map, and this is also a beautiful relation. Now, these two relations, they look actually very different. They are a bit weird. One is linear, the other is quadratic. However, although they look extremely different, it turns out that they are basically the same relation. So if you want to prove KLT, the way KLT proved these relations in their original paper was by doing something that we denote by holomorphic factorization. So basically, you take this integral over the complex plane, and then you write it like this, and then you start deforming contours, and you write these two integrals as two integrals over the real line or over the segment from 0 to 1. And it turns out that Francis Brown has proven that the same procedure implements the single-valued map when you represent all these polylogs, etc., in terms of these integrals. So that actually, the KLT relations and the single-valued map are the same thing and are the same relations. Okay, so they look different, but for a mathematician, they basically look at them and they say, oh, that's the same thing. I don't see any difference. Is that okay? So this is quite cool. Beautiful. So this is basically what I wanted to say about the story in flat space. And now something that is a very natural question is how much of all this story generalized to EDS. Okay, so this is the answer, the question we want to answer. So this involves basically two parts, this process. So the first process is to try to compute amplitudes in EDS, which is non-trivial. And once you compute them, we start checking what are their properties, etc. Okay? But before I go ahead, do you have any questions? That's good. Yes.
Well, you mentioned the Regge behavior before for in flat space-time. Can you anticipate what would be the Regge behavior for ADS?
Yes. Yes. Actually, yes, I can actually, and that has been worked out, and I can tell you. Yeah, I can show you in formulas later, but yeah, that's true. Yeah, I mean, yes, I can be much more precise later about this. It's a super interesting question.
Hi, I wanted to ask you about the single-valued map that you showed us. So you said that the single-valued map applied on the open string amplitude gives the closed string amplitude.
Yes.
So I wanted to ask if you can see something like this at the level of the spectrum and structure constants as well.
Oh, that's a beautiful question. I have been wondering myself the same question. Now, you will see that, sorry, in flat space, the spectrum is a bit too simple. and
Sure, yeah, no,
yeah,
I mean
while in ADS we don't have yet a version, but I will talk about what we have. And yeah, that's a very interesting question actually, is what kind of relations for the spectrum, which they should imply something, right? Like if you have a relation, then they should, like you could look, for instance, at these sort of relations, and then you look at the poles on both sides, etc. Yeah, that's a good question. Okay, so now in curve backgrounds, in the presence of Ramon backgrounds, we actually, in general, we don't have a worksheet theory, so we are a bit screwed. But for the special case of ADS 5 cross S5, we can make a lot of progress by using many ideas from many directions. And we can use integrability, bootstrap ideas, number theory, and that's what I will describe in the second half of my talk, okay? So the first tool that we use, of course, is the ADS-CFT correspondence. So the ADS-CFT correspondence gives us a working definition of string amplitudes on ADS as given by correlators of local operators in the conformal field theory at the boundary. And in this case, because we are interested in computing 4-point amplitudes, we will be looking at 4-point correlators. This is actually very general, but we will look at a very specific example, and I will list later other examples for which this has been worked out, that relates a string theory on ADS 5 cross S5 to 4D n equals 4 super-Jenny Mills, and that's super familiar to everyone in this room. We know that this correspondence gives us also a dictionary between the parameters on both sides. So for instance, the string coupling constant GS is basically 1 over n, where n is the number of colors for a SUN gauge group, while the common radius of ADS5 and S5 in units of alpha prime is related to the square root of the top coupling G-Jan-Mill square n. So that we can make a slightly more refined version of this dictionary. So for instance, we see that the genus expansion, the small GS expansion in terms of the string amplitude, corresponds to a 1 over n expansion in the n equals 4 super-Jenny Mills case, while string corrections to supergravity, or a small alpha prime expansion, correspond to a 1 over lambda expansion on this other side, just by using this dictionary. On the other hand, if we want to scatter gravitons, that is what we want to do, then the duality tells us that we should consider the correlator of a scalar operator of dimension 2 in the stress tensor multiplet, which is basically the simplest operator in n equals 4 super-Jenny Mills. So what we need to do, we need to take 4 of these guys and then try to compute this correlator in n equals 4 in a 1 over n expansion. Okay, so that's it, basically, and we would be done. So the observable, if putting a bit the indices, just to ignore them 2 lines later, the observable has some R symmetry. So these operators have some R symmetry indices. They transform in the 20 prime of this SO6 R symmetry. But luckily, the dependence on these R symmetry indices is fixed by the supersymmetric word identities. And at the end of the day, we end up with a prefactor times a function GUV of the 2 cross ratios that we usually consider in conformal field theories. And because this is a Bootstrap conference, I don't need to say much more. But notice something that is quite nice. Notice that this structure is very much the same as the structure of the scattering of gravitons in flat space. Sorry. Which was this structure here. And this is, of course, not a coincidence. Okay? Good. Sorry. So we need to consider now this function GUV, which is a function of the cross ratios. And what makes this computation extremely hard is that this GUV is a highly non-trivial function of n and lambda. For instance, you know that if you had this function of GUV, by studying the conformal partial wave decomposition, you could have the whole spectrum of intermediate operators of n equals 4, and that's something, you know, huge and massive. So all that information should be repackaged into this very little function, GUV. So this is a beast, and it's a very complicated beast. Now, because we are interested in three-level amplitudes, which, remember, corresponds to a 1 over n expansion, we will consider the leading non-trivial term in the 1 over n expansion. Now, this function that we call G3 UV is still a highly non-trivial function of lambda, but this is the function that we are trying to compute, okay? And this is the function that in some expansion we will be able to compute. Now, first, we change language. So there is a language which is called Mellin space, in which this correlator looks much more similar to an amplitude, okay? So I told you that amplitudes in EDS, they map to some correlator, but there is actually a language developed by Mack and Penedones in which the correlator looks really like an amplitude. And this language is Mellin space. So you start from this function of two cross ratios, and you define this integral transform with this prefactor given by some gamma functions, and this object here is what you call the Virasoro-Shapiro amplitude in EDS 5 crosses 5, where these three, now called Mandelstam variables, Mellin variables, are chosen such that S plus T plus U is equal to 0. Now, this is a formulation where the correlator looks much more like an amplitude. For instance, something that you can do is to take this correlator here and compute it in a 1 over lambda expansion, okay? So this is the so-called supergravity result. In EDS, it looks like this, and it was computed many decades ago by Frolov and Aryutunov, and Frolov, and it took several decades to compute the next terms here. So this is a very hard computation. So the first term is the supergravity, the result in the supergravity approximation, and then we have a 1 over lambda expansion in which we have symmetric polynomials on ST and U of higher and higher degree. But notice that as opposed to what happened in flat space, these symmetric polynomials are not homogeneous anymore because we have another scale now. We have the radius of EDS, okay? So this expansion looks a bit similar like the expansion of the Virasoro-Shapiro amplitude, with the big difference that now these polynomials are not homogeneous, okay? And fixing these coefficients is what we will try to do. Now, for finite lambda, this function Fm of S and T should be a meromorphic function with very nice properties, okay? And these are the properties that, that we have. So first, it should be crossing symmetric under the exchange of S, T, and U. The second, due to the conformal block decomposition, exchange operators should correspond to simple poles of the following form, like this. We also have a Rege limit, which is given by this, and in the flat space limit, which I will define in a bit, it should reduce to the usual Virasoro-Shapiro amplitude. Now, something that I would like to warn you, this list is deceivingly similar to to the constraints in flat space. So in flat space, we had a very similar list. Sorry. We have a very similar list like this, but this list somehow is much simpler than the list in ADS, okay? But the plan would be the following. Imagine you are Virasoro, okay? If you are Virasoro, that's a good fantasy, but imagine for a bit that you are Virasoro, and you don't know the answer, you only know these properties here, okay? Then he was able to guess, basically, this answer from these properties. Now, in ADS, the conditions, they look similar, but they are way, way harder. So for instance, something that you can see is that, for instance, here, exchange operators lead to simple poles. So in the conformal case, in ADS case, for a given primary, you have an infinite sum over all the descendants that corresponds to this M, and the polynomials here are much, much harder than the polynomials that appear in flat space. They are Mach polynomials. And right, so because of that, this list of constraints is way harder to deal with. But basically, the Bootstrap idea, or the idea of this project, is can we guess what is the result by looking at this list of constraints, okay? And the answer to the question, can we use these constraints to fix this M3 ST, the ADS Virasoro-Shapiro amplitude, is actually yes, but we need to make one more assumption, which is crucial and really strong, okay? So in order to tell you what this assumption is, let me tell you a little bit about this flat space limit. So the flat space limit, yes. Right, so you can use crossing symmetry, etc. So there are different things. Yeah, I was also thinking almost not writing this. So to prove all these things, in a conformal field theory is quite complicated, but you are correct. And the paper that proves all this is called conformal rigid theory. So the answer is yes, and that was done in a paper by Penedones and Costa. You just yes. So there is you just need to you do some contour deformations, and there are some things at infinity that you can throw basically if this is true. Yeah. So from that paper is quite clear, but it's very technical. Yeah, it's a bit technical, but it has to do with contours that you are dropping, etc. Good. So let me tell you now about the flat space limit of this. So the flat space limit is a limit basically where we take the radius of ADS to be very large, but at the same time, we take the Mandelstam variables, ST and U, the Mellin variables, sorry, also to be very large. And what one can show is that in this limit, it's like the interaction happens on a very small region of space-time in the bulk of ADS, and because of that, it doesn't matter if at the boundary we have ADS or flat space. So basically, one takes the limit in which ST and U and R are all very large, with S over R squared, or S over square root of lambda, being fixed. And notice that if you take that limit, what happens in that limit is that in this expansion here, you keep only the leading order terms, okay? So you are taking a double scaling limit where S and lambda are large, ST and U and lambda are large, such that at each order, you only keep the leading terms of each polynomial. So here the degree 2, here the degree 3, and so on. Okay? And then what happens is that if you resum all these leading pieces, you take this, plus this, etc., that should basically be the Virasoro-Shapiro amplitude in flat space. So that after rescaling S and T with the square root of lambda, we can write down the same answer, but now as an expansion around flat space, where first you take all the leading order terms in each polynomial, then you take all the subleading order terms, the sub-subleading, and so on. So the first term, the first piece, will be the Virasoro-Shapiro amplitude in flat space, then the first curvature correction, the second curvature correction, and so on. Okay? So we can do that expansion as well. Now, each bit, each of these little pieces, admits itself a low energy expansion, which, for instance, for A0, we know what it is. It is what we saw before, the Virasoro-Shapiro amplitude in flat space, while for A1, we get the first term that comes from gravity on ADS, and then a bunch of infinite number of unknown coefficients, and so on. And here, it comes the critical assumption. We will assume, and we don't have a way to prove that, we will assume that all these unknown coefficients are single-valued zetas. They are not whatever. They have to be single-valued zetas. That's our assumption. Okay? Beautiful. Yes?
So I have two questions. So first of all, is the planar single trace spectrum useful input at all for you?
Yes. At some point, I will talk about that.
Okay.
Yeah.
I guess you're saying this is just an assumption, but of course there's some kind of naive picture of inserting vertex operators involving
Absolutely.
a polynomial
Yes.
of the
Yeah.
say the boson fields.
Yes.
I mean, from that kind of logic, one might think that sort of this kind of single value zetas would appear in any kind of expansion around flat space, not just ADS.
Yes, I fully agree with both things. Yes, that's true. Yeah. So yeah, I agree with that. And actually, we had a picture of kind of understanding this in terms of adding extra gravitons. And in that picture, you don't use the details of what the curve background is too much. Yeah, 100%. Yeah. Beautiful. Very nice. So it turns out that this assumption is actually very powerful. So now the list of constraints, so now to the list of constraints we had before, 1, 2, 3, 4, we add this number 5, that is that the low energy expansion of M3 contains only single-valued zetas, okay? So all these are proven, rigorously proven. This one is not, but it's what we are adding in order to make progress, okay? Now, it turns out that this assumption is extremely powerful when supplemented with the correct structure of poles. Now, remember that I told you, and we saw, that the amplitude in flat space, the Virasoro-Shapiro amplitude, contains single-order poles. One can actually see that corrections are more complicated. And in particular, this A1, the first order correction to the amplitude in ADS, contains quartic order poles. This may seem a bit surprising, but actually it simply, okay, I didn't want to spoil that. But actually it follows if you carefully look at this in this flat space limit properly defined. So that actually, in general, we have that this object here, the flat space amplitude, has single order poles. This has quartic order poles. This has poles of order 7, and so on. Yes? Well, no, I don't. Well, I don't think I am assuming that. But this is a bit technical. But yeah, okay, fair enough. Yeah, I mean, okay. So you could see you. Okay, so the one question. The question is the following. If I can rephrase the question a little bit, is that here. So the only claim in the literature is that if you take the flat space limit, as I kind of describe here, there is an integral transform, but I didn't want to enter into this technical detail, then this leading order term corresponds to the amplitude in flat space. I am taking this procedure literally, and I am saying that curvature corrections to that are also computed by the same procedure. And this is the question by Shai and the assumption. Actually, the way I see this is that you have always the right to repackage your amplitude in any expansion that you want. And what I will show is that if you write things like this, then there is a nice way to compute A1, A2, etc. So I am not sure if this will be the way that the true amplitude in ADS will be repackaged. This I don't know. However, this expansion is in one-to-one correspondence with the correlator that we started with. And maybe there are other ways to repackage things that will make some structure even nicer. That I don't know. But this is a repackaging that we can always do and with which we can compute. Oh, the reduce. No, well, sorry. So once you compute the reduce in any way, you can always find the full one. I can tell you what the full correlator is in this expansion. It's not that the algorithm doesn't work. So I am giving you an algorithm where there is a way, a more or less systematic way of computing these 1 over lambda expansions. There could be a different way, but this is a way. And in this expansion, it gives you the correlate. It's in one-to-one correspondence with the correlator.
Isn't this just effective field theory?
Yeah, for instance, yeah. But of course, that, like in effective field theory, you could do redefinitions that will shift this A1 by something proportional to A0, all these sort of things. But yes.
But that's okay. You're allowing that. You're allowing for that. I mean, I'm just saying that the structure of this expansion just follows from effective field theory. You know?
Yeah. I think it's a very natural assumption, and it's an assumption in which we can compute all these things. But maybe there is like a slightly reshuffled formulas for subleading terms that work better, etc. Yeah. Good. Very nice. Sorry, so let me see where we were. Beautiful. So now, I have 27 minutes says here, but maybe 15. Okay. Well, I started a couple of minutes late. It says 27 here. Okay. 12 should be okay. Okay, good. Let me go then. Beautiful. So basically, we know the fact that in the expansion, we have only single-valued zetas. We have the structure of poles, and we have some intuition or hope or dreams that there will be a worksheet and behind this computation. And basically putting all these things together, we make a proposal order by order for the form of these corrections. And for instance, we have seen that the first correction, A0, admits this integral, this worksheet representation. And notice that, for instance, if you want to add something that produces quartic order poles, something that you could put is a log cube of z bar. Because log cube of z bar is like taking 3 derivatives with respect to S, and if you take 3 derivatives with respect to S of a single order pole, you get a quartic order pole. So our proposal is that A1 is given by the same integral representation with the extra insertion of single-valued polylogs of weight 3. And in the same way, A2 is given by the same worksheet representation with single-valued polylogs of weight 6. We have 4 different ways of understanding this. I don't have time to describe any of them, but basically many different ways. They all lead to the same structure. Now, once you believe in a proposal like this, you are on fire. And the reason you are on fire is because here we have to fix an infinite number of coefficients. An infinite number of coefficients. But here, there is only 8 polylogs of weight 3. So you have to fix 8 coefficients. And it turns out that the structure of poles is so powerful that this W3 is fixed uniquely. And basically, what happens, so before I go to the end, so let me quickly tell you this, and then I want to discuss open strings in ADS, is that the pole structure fixes W3 completely. For W6, you need to use a bit more, like for instance, some localization results, etc. And you see that all the properties that I listed above are actually satisfied. But now, there is also a beautiful surprise, because if we computed a 4-point amplitude in ADS, we can now look at the poles of this amplitude, okay? And looking at the first pole of this amplitude, we see that there is an operator whose 1 over lambda expansion is exactly like this. And then we ask people of integrability if they have seen that, and this is precisely the dimension of the Konishi operator. And we even produce Konishi with higher spin. Now, in general, there is a game that one plays. One has several undetermined coefficients, and you can use either localization constraints, and then you get this, or you can use this, and then you get localization constraints. But there are several non-trivial checks, just to answer to your question.
Is it because it's the unique non-BPS multiple at this level? I mean, generally there will be some degeneracy, and the reason you can fix it is because there's no degeneracy?
Right, so for the leading Ricci trajectory, there is no degeneracy, so one can read off this. Now, actually, Julius, in the audience and collaborators, they have also studied the next Ricci trajectory, and you can also infer things for the operators of twist 4, like for the ones above. And there is some degeneracy, but you can solve some of this degeneracy. And, yeah.
So another question is, are these zeta values something that you would expect from the strong coupling expansion from the quantum spectral curve?
Yeah, they appear.
So that's something known.
That's something known, however, okay, so one needs to use these dispersive sum rules to relate the CFT data to the Wilson coefficients of this low energy expansion. And then in addition to the anomalous dimensions, which are kind of known, you also have OPE coefficients. But you are basically right that there seems to be a one-to-one correspondence between the structure of CFT data in planar n equals 4 super N mills and the fact that these things are single valued. But it's more involved than this. And it also involves 3-point functions like these OPE coefficients. So now, perhaps in the last like 5 minutes or 6 minutes, everyone went over time, and I think I will take 6 minutes. Okay. Fair enough. Okay. So now the idea is to scatter open strings. And if we want to have open strings, then one adds brains to the construction on ADS 5 × S5. And if we do this, then what happens is that we break n equals 4 super-Yanni-Mills into n equals 2 super-Yanni-Mills with flavors, okay? In very much the same way, so now the theory is a theory with n equals 2 supersymmetry, but you can define a Mellin amplitude, and this Mellin amplitude again admits a curvature expansion like this. Now, notice that in this case, the situation is a bit different to the scattering on ADS, because in ADS, for closed strings, we have single valuedness, while for open strings, we don't, okay? However, we also, for closed string amplitudes, we have this form, right? We have the same Virasoro-Shapiro amplitude times some insertion of single-valued polylogs, so that actually, for open strings, we have also a very clear proposal, okay? And the proposal, what we are going to do, is that we take the integrand for the Veneziano amplitude, and instead of single-valued polylogs, we will insert harmonic polylogarithms, okay? And it turns out, I don't have time to explain it, but it turns out that the structure of poles for these open string amplitudes, the curvature corrections to the open string amplitudes, is very similar to the case of closed strings. And then our proposal is that the open string amplitude in ADS is given by precisely the integrand of the Veneziano amplitude like this times the insertion of harmonic polylogs of weight 3, 6, and so on. And this is, notice that now these functions are multivalued functions on the complex plane, but we are not integrating them over the complex plane. We are only integrating them between 0 and 1, okay? And okay, so we see that again, the structure of poles is super strong, and we can fix even the next correction up to one coefficient that can be fixed by using localization results. And the final expression passes non-trivial checks. So now I go to the conclusions in 1 minute, if that's okay. So by now, this has been done in a variety of backgrounds. Notice that the building blocks are in the closed string amplitude is this integral over the complex plane with the insertion of these single-valued polylogarithms, while in the open string case is the Veneziano amplitude with these multi-valued polylogarithms. And there are many relations between them, and one beautiful relation that is some KLT version of the relations in ADS is that these integrals and these integrals are again related by these quadratic relations that are the KLT relations on ADS, and one is the single-valued map of the other. So let me now go to the conclusions. I'm sorry for being extra, for being a bit extra time. So we have two types of questions. So there are some medium questions. For instance, is the conjecture correct? And do we need to enlarge the family of functions that we use? Now, can we solve the next order? And can we find some patterns? Are there double copy relations in ADS? And notice that we have worked out the relations for the building blocks of the amplitudes, but one would need to check explicit amplitudes to see if one is a double copy of the other. But then the most interesting question, I think, is the big question, is whether we can reproduce this from a worksheet description for strings on ADS5 x S5. And two very promising approaches, one would be trying to use string field theory or trying to use the pure spinor formalism. It would be very nice, I think the question of Xi, to try to kind of relate this to the quantum spectral curve, and perhaps we kind of have a curve for the whole amplitude. It would be nice to understand the nature of the 1/r expansion, and if it has perturbative corrections, etc. Genus 1, and also ADS amplitudes for massive states. Thank you very much.
So have you guys checked what happens in the case of PP wave background?
Yeah, that's very interesting, actually. Okay, the quick answer is no. Now, sorry, by check, I don't know what check is, because like the question is whether you could do the computation or not. Yes. And we don't have so much of the technology developed that we have used here. Now the operators that the external operators we are using, they have some small R charge. One could go towards the PP wave direction by consider 4 operators of very large R charge. That could be interesting to do, and it relates to Coronado and Pedro, things that they have been looking at. But yeah, yeah, it would be nice, and I think it should be possible. But in this case, the R charge of the operators is much smaller than the other scales we are talking about. The R charge, the R, the radius R, etc. Julius and Nathan.
Hi. So for the open string case, you don't have single valuedness anymore. So that means your basis is much bigger?
No. Right. That's a very good question. Notice that there is a one-to-one correspondence between, I think this is a very good. So there is a one-to-one correspondence between harmonic polylogs and single-valued polylogs. And indeed, the basis is always integrals like this, where for the closed string case, you have the single-valued ones, and here you have the multi-valued ones, but their label, omega, is always the same, and are words from the alphabet 0, 1, in this case of length 3, length 6, etc. So actually, the number of independent coefficients, let's say, is more or less the same. Oh, that would be amazing, actually. Okay, I have conjectures for many things in 5 points. They are all in my head because I didn't write any of them because I don't feel comfortable enough. However, yes, and the fact that basically there are many things that are very clear, for instance. So here you have that the words are 0 and 1 because you are putting operators at 0, 1, and infinity, so that if you have an extra operator, you will have to increase that to multi-polylogs, where now you have 3 letters. Where the right. So the details. That's why I haven't written a paper on them. So on it, yeah. So the details of how you solve the word identities, etc., are way different. However, by the time you get here, the structure should be very much the same, where the number of letters, where this alphabet gets enlarged. And you can see some things, for instance, in the high energy limit. You can compute the closed string amplitude in the high energy limit. And you can also have a look at the computation by Gross and Mende, and their computation generalizes easily to higher points. So in that limit, I would expect to get something like this, for instance, yeah.
So am I understanding correctly that so far the results are up to order alpha prime squared?
Right, so, well, we do this expansion. So basically, yeah, I think I think the best, sorry, so just 1 second. Right, so basically, if you take any arbitrary order here, so we have A1, A2, and basically this means that at any order in 1 over lambda, we know the leading term in the polynomial, the subleading, and the sub-subleading. That's the 3 things that we know.
Okay, and do you see any obstacle in continuing to next order?
The number of terms. And I think Tobias has tried, and there is something, you said like 1,500 coefficients, right? Right. So yeah, but we have learned a little bit in the meantime. But yeah, so the last time Tobias tried, we had 1,000 arbitrary coefficients, and all of them are fixed up to 70. Yeah. So I don't know. We need a bit of some input, I think, if we want to go to the next term.
So I was suspecting that there's something kind of qualitatively non-trivial going to next order, because if you consider the Green-Schwarz action, up to alpha prime square order, I think there's no room for counter terms that are compatible with space-time supersymmetry. But once you go to the next order, I think there is, because it's analogous to D4 to F to the 4th term correcting the DBI action.
Sorry. So this reshuffles a bit the. So here there are many unprotected things we are computing, right? So here we are computing at each order in 1 over lambda. We have all the leading, the next one, and the next one. So we are already computing a lot of non-protected things.
I understand, but I'm talking about ambiguity due to, okay, so I think this approach seems to be not a priori sensitive to the UV completion of the worldsheet theory, I would think.
Although we use the structure of poles, dispersion sum rules, and many of these things have to do with the UV completion, right? The Regge behavior.
Yeah, I guess I was thinking about how to, if one imagine trying to do this combination just from the Green-Schwarz approach, then one would expect the ambiguities at the upper prime cube order.
Yeah, could be, yeah.
Okay.
I mean, I guess maybe we can fix all the parameters except some ambiguities, and these ambiguities we cannot fix from this alone. Yeah, it's very possible indeed, yeah. Thank you.
Announcement is Monday, we start at 9:30 and not at 10, sorry.
Okay, very good. So it's a pleasure, a bittersweet pleasure, of course, but great pleasure to have Shi give the very last talk of the conference.
Thank you very much for the opportunity to speak and for, well, let me speak in this last slot. So I'm going to be talking about, well, the title is called The Unreasonable Effectiveness of D-instantons. It's going to be about D-instantons in string theory, but it's also going to have some, hopefully, connection to questions purely concerning quantum field theory, as I will explain shortly. This is going to be based on upcoming work with 2 students, both of which just finished their first year of grad school, Yaroslav Scheinpflug and Yuchen Wang. Yaroslav is expert in string field theory, but for this project is in fact, Yuchen Wang is actually the person who has been leading this effort, and my own contribution mostly is to complain about factors of 2 and signs. Let me, and I'm going to try to keep this, I see a kind of a broad audience. I don't want to, be overly technical in much of this talk, but it is kind of a technical subject, so some technology will have to be introduced. But let me begin with just the general picture of what is the physical question we're after. We're going to consider the most canonical setup of D-branes in string theory. Let's consider, well, this is better. We're going to consider just in type 2b, Minkowskian, and D3 branes. And we all know that in the low energy limit, let's say the alpha prime goes to 0 limit, the Ward volume of the ND3 branes reduces to the 4D n equals 4 super Yang-Mills theory, which many of us here care about. I'm going to be mostly concerned with not taking the alpha prime goes to 0 limit, even though I believe what I'm going to say also have non-trivial implication that is yet to be uncovered even in the alpha prime goes to 0 limit. Regardless of whether we take the low energy limit or not, we can discuss the dynamics of open strings on the D3 brane and the scattering of open strings. Now, in string perturbation theory, you can, of course, calculate, the open string amplitudes perturbatively through worldsheet diagrams of topology of the disk and the annulus and one-hole torus and so on and so forth in a perturbative expansion. But then there are also, in principle, non-perturbative effects. And a class of non-perturbative effects in string theory that are, there's a sort of that has a kind of a bit of a history, which I'll explain in a bit, would be the so-called D-instantons or D-1 branes. I'll just call them D-1 instantons, or D-instantons for short in this case. I mean, there can be more general D-instanton than D-1 branes, as Liam had actually mentioned in his talk. I guess that was Wednesday. We also know that in n equals 4 super Yang-Mills, if you study some either coordinate function or, say, scattering amplitudes on the Coulomb branch, you can do perturbation theory in G Yang-Mills, but then there are also non-perturbative effects in the gauge theory. And those are the, let's say, the Yang-Mills instantons, which we usually think of as, say that this is a saddle point of the path integral, and the description of the Yang-Mills instanton is that it's a Euclidean gauge field configuration in R4 whose Lagrangian sort of concentrated in some finite region of space. Now, just by sort of a kind of a naive back of an envelope estimate, you expect that so the D-instantons and the Yang-Mills instantons are very similar. Indeed, one expects that the kind of non-perturbative effects in the string theory mediated by the d-1 branes, or d-instantons, sort of, roughly speaking, are in correspondence with the effect of the gauge instantons. But in practice, how you would actually calculate such non-perturbative effects would be totally different on the two sides. So the gauge instance is treated as a saddle point of the path integral. To the extent that we understand, we think the path integral is non-perturbably defined, it has some measure, you can, whenever you get confused, you can always go back and think about the lattice. We believe the Euclidean lattice gauge theory in the continuum limit does reduce precisely to the UV complete asymptotically free. Well, sorry, I guess I was thinking about the ordinary Yang-Mills theory, but at least in the context of bosonic Yang-Mills theory, you can always go to the lattice definition whenever you're confused about this non-perturbable definition. And to the extent you have a non-perturbably defined path integral measure, you can identify the saddle points that might mediate the essential non-perturbable effects of your interest. And in order to actually calculate that instant contribution, what you usually do is that you want to consider a perturbative expansion of path integral around that saddle point, the Yang-Mills instant saddle point. You will organize the fluctuation modes of your field in terms of the zero modes, which correspond to typically the collective coordinate of the instanton, and the so-called quote-unquote massive modes, which in optimistic situations will be controlled by a effective action that is a Gaussian plus corrections, and then you can then do perturbation theory around that Gaussian. And then after that, you integrate over the zero modes, which amounts to an integration over the moduli space of the instanton. And usually the most difficult part of this calculation is to pin down what the measure is in terms of these variables that characterize the modes of the field fluctuation around the instanton configuration. So that's what we normally do in the gauge theory. But with the exception of few kind of heroic calculations, most of the time we kind of cheat a little bit. We don't try so hard to fix a normalization. Now, on the string theory side, the description of the d-instantons, at least, is totally different. There is no path integral of string theory to the extent we know it that can characterize the d-instanton as a saddle point of some field configuration. Rather, this terminology of d-1 brane refers to the fact that the d-instanton is defined from the point of view of the worldsheet theory as some kind of boundary condition for the worldsheet theory, just like a d-brane, except that it has -1 warp volume dimensions, which just means that the total warp volume direction of this brane, it has 0 plus 0 dimensions. It's a object localized in both space and time. So if you think about the worldsheet theory involving, let's say, 10 bosons for the type 2b string theory, this d-instanton will be characterized by a boundary condition of the worldsheet. So let's say this is the string worldsheet, and the d-instanton will be characterized by a boundary condition of the worldsheet that says that the end of the string that are stuck on the instanton are going to be localized at whatever point that specify this location of d-instanton in space and time. Now, exactly what the d-instanton is, just like the position of Yang-Mills instanton is a collective coordinate that you ultimately have to integrate over. And you might imagine that if you do the appropriate integration, you would get the appropriate non-perturbative contribution to a scattering amplitude. In this case, talking about open strings. Now, in fact, the unambiguous computation of the d-instanton effect on string amplitudes, in the sense of kind of a perturbation theory around a saddle, so to speak, is only something that was that is starting to be understood with thanks to the work by Ashok Sen in 2020. And now, at least in simple cases, we have a first principle way to pin down these d-instanton contributions. But the method that I'm going to describe to pin down these computations are completely orthogonal to the method we're going to use in the gauge theory. Which suggests the interesting possibility that if we actually just take the alpha prime goes to 0 limit, we're going to actually learn something new, even just about the gauge instantons. That has not been done, so that's not part of the work that's going to appear. The work that we have actually done so far is the n equals 1 case. So this n is a rank. So I'm just going to consider a single D3 brane. And of course, in this case, the interest is not the low energy field theory, which is a free abelian theory. We're interested in the full effective theory. Let's say the massless effective theory of the D3 brane, but the full quantum level. So this effective, the quantum effective action is just by the general expectation of effective field theory is going to be the form the dBi action plus some higher derivative corrections in either Wilsonian scheme or in the context of the 1pi effective action. Schematically, you can think of the so very, very schematically, you can think of the Lagrangian as so you have some non-abelian Maxwell theory at 2 derivative order. The dBi will tell you that you have some f to the 4th term. There are going to be some f to the 6th term, and so on and so forth. Supersymmetry will constrain this effective theory in such a way that the first possible higher derivative correction to the dBi action will be schematically d to the 4th f to the 4th. And by that, I just mean a term in the Lagrangian that has 4 powers of the field strength and 4 extra derivatives with some appropriate tensor contraction of the tensor indices, and that contraction is unambiguously fixed by supersymmetry. And of course, there's the supersymmetric completion of this involving all the other fields, which I am not going to write explicitly. So for instance, if you study the scattering of 4 gauge bosons on the D3 brane, it will be, in a derivative expansion, it will be captured first by the f to the 4th term in the lowest order in the momentum expansion, and then you have the d4 to the f4th, and so on and so forth. It is known that this f to the 4th coefficient is protected essentially by a combination of supersymmetry and soft limits. So it does not have non-trivial dependence on the string coupling. Whereas the d4 to the f4th coefficient a priori is a function of the string coupling, or more precisely in type 2b string theory, because the Minkowskian vacua of type 2b string theory is characterized by this complexified coupling tau, which is the Riemann-Roman axion, plus I over the string coupling. This coefficient d4 to the 4th term, which is the first non-trivial correction to dBi action, will have some non-trivial tau and tau bar dependence. So the name of the game here is going to be the particular thing I'm going to be talking about is to study this coefficient, the d4 to the 4th term that corrects the dBi action at the quantum level. But this is really just a kind of a test. A part of the purpose of this is also just to test the technology. But there's going to be a surprise. So I want to emphasize that this term, to the best of my knowledge, is not protected by supersymmetry. There's no non-realization theorem that controls the coefficients, control the tau and tau bar dependence, and we do not expect any, because this is sort of the first D term. If you write kind of from the superspace point of view, it's like supposed to be the full superspace integral, and so there's no known supersymmetry constraint on the tau and tau bar dependence. Nonetheless, there has been a conjecture many years ago by Green and Gutperl on this function. So I'm going to come to that, the details of that at the end. I will tell you what are the results, and there's going to be some, at least a small surprise at the moment. But for the bulk of my talk, I'm going to discuss the general logic of the technology goes into this computation, which is going to be based on string field theory. And the string field theory is sort of the only game in town, because the only way we know of that can systematically categorize such D-instant effects. So, are there any questions before I get into the string field theory? Yes. Oh, thanks for that question. That's an excellent question. Yes, but in a very minor way. In fact, what happens is that at this A-derivative order, this contribution of this to the amplitude would be mixed with a one-loop amplitude where you have f to the fourth vertex, and sort of a contribution to one-loop amplitude. Contribution to amplitude that have to do with the unitary cuts into a pair of f to the fourth vertices. That has a contribution at the same order as the d4 to the f to the fourth term. That will lead to a small ambiguity, and you'll see explicitly where it is in the formula. But it's not going to affect much of the discussion. Any other questions? Okay. Let me actually. There's one more comment I meant to make. The idea of concerning the motivating remark, the idea of relating the D-instanton description to Yang-Mills instanton is not new. This goes back to the 90s. Ever since the D-branes were discovered. It was shortly after it was observed that there's a way to understand at least the moduli space of the Yang-Mills instanton using this D-instant description. So let's say in the past, let's say 90s, it was known that the massless EFT of the D-1 D3 system. What do I mean by that? Well, it's a little funny to speak of effective field theory that involves degrees of freedom on the 0 plus 0 dimensional Ward volume. But what this EFT is that it's in fact very similar to the effective field theory on sort of D-brane within D-branes of higher dimensions. Let's say D3, D7 system. You can have D3 brain sitting within a Ward volume of D7 brain, or let's say D1 brain sitting in a Ward volume of D5 brain. As long as the codimension is equal to 4, we expect the system to preserve a quarter of the 32 supersymmetry, so it will be an 8 supercharge effective field theory that you can categorize the low energy effective Lagrangian in terms of some vector and hypermultiplets. So this massless effective field theory D-1 D3 brane, which in some sense can be viewed as a low energy limited open string field theory, but as I'll say very soon, it's a bit imprecise. That point of view is not totally precise, but nonetheless, so people view this effective field theory or derive this effective field theory simply as a dimension reduction of the effective field theory on, say, the D1, D5 system. The D1 brane embedded into D5 branes. And then you just reduce 2 dimensions. So, so at least heuristically, that effective field theory is supposed to characterize low energy in a certain sense, effect some kind of low energy effective action of the open strings with both ends on the D-1, or with one end on the D-1, the other end on the D3, as well as open strings with both ends on the D3 brane. So there's this whole system of massless open string modes, and they interact through some action. And by studying that effective theory, one uncovers the so-called ADHM description of the gauge instanton of the, let's say, the Yang-Mills instanton moduli space. This moduli space just says what are the possible configurations of the saddle point given the instant charge. But the modular space is by no means the complete information we would like to know about the instanton. We want to know much more. We want to know what is the actual non-perturbative effect mediated by the instanton, and that you cannot learn just from the knowledge of instant modular space. So the upgrade of this, which is essentially due to Ashok-Sen, and from 2020 and on, is well, strictly speaking, Ashok did not apply that to the D3 brane case. That is the work we are describing here. But the general formulation of the instanton was developed by Ashok. The idea is to use the open string field theory, which is kind of an upgrade of the master's effective field theory, to use the open string field theory in this case of the D-1 D3 system to produce the full, let's say, instanton contribution to the, let's say, to the gluon, in this example, the gluon amplitudes. Okay, so that's where we're going. In fact, let me make sure I understand. I'm not sure if I actually completely understood the question. So the question was about. Okay, I think Mukund's question was originally this was to understand the non-abelian instanton, but here I'm focused on this abelian case. What I'm trying to say is that the same strategy would also work for ND3 branes, but we just haven't done that work yet. So far, there's plenty to do, even in the case of single D3 brane. And the goal here, of course, isn't to understand the modular space instanton, but simply to understand the actual instant contribution to a scattering amplitude.
Okay, that makes sense. Thanks.
Okay. So I want to say a few words about string field theory. I'd like to say briefly what it is and what it is good for. Now I think not everyone here is probably super familiar with the worldsheet formulation of string theory. Now, very often, you might think of the worldsheet theory in the sense of an effective string, right? Some effective action, then we go to plus high degree terms, things like that. Say in the case of Pierre-Yamil's theory in 4 dimensions. For my discussion here, this is going to be in the context of critical string theory. So it's going to be essential that worldsheet theory has a UV complete description. And this worldsheet theory, in the usual on-shell formalism, is viewed as 2D gravity on the worldsheet, and typically we fix the gauge to conformal gauge, and the conformal gauge you have a conformal field theory with the ghost system. And we often speak of the worldsheet theory as the worldsheet CFT, quote unquote, but I want to emphasize that, at least in the context of critical string theory, that is a very much imprecise way to think about worldsheet theory. It should really be viewed as a worldsheet theory of gravity. It's not just the CFT. The CFT only captures an aspect of it, but for what I'm going to say, the ghost structure is going to be absolutely essential. So I'll say a few more words about that. So we begin with the worldsheet, let's say the super conformal field theory with ghosts. I will say what the ghosts are, what the ghost system is, in both the bosonic string case and the superstring case, which is going to be the case of interest here. Now, this worldsheet theory of the string is going to be defined in a given space-time background. So, in the case of the type 2B string theory, for the Minkowskian background, we have a particular worldsheet theory that involves some free boson, free fermion, and some appropriate ghost system. The string field, what we call the notion of the string field, which I will typically denote by capital psi. This ink is getting weak. The string field, so what is a string field? The simplest way to characterize it is just a state vector in the space of states of the worldsheet CFT with the ghost included. Now, as physicists, we often abuse the terminology and refer to this as a Hilbert space, even though with the ghost system, of course, there's no canonically defined positive definite inner product. So just the space of states. In fact, the precise notion of normalizability on the string fields is not something that has been understood, but that's a the kind of issue that would brush under the rug for the purpose of what we're going to discuss. Now, a few kind of comments about this. So it is essential that we include ghosts. So just as an example, the critical bosonic string theory, for which the string field theory is only supposed to make sense at the classical level, but nonetheless it does make sense at the classical level. The worldsheet theory would include this worldsheet CFT would include 26 free bosons and a decoupled BC ghost system, while the BC ghost system consists of some holomorphic field operators denoted by B of Z and C of Z, where Z is the complex coordinate on the worldsheet, and anti-holomorphic counterparts, C tilde. These are, with back to the Virasoro algebra, these are conformal primaries of weight 2, 0, and minus 1, 0, and 0, 2, and 0, minus 1. The BC ghost system has central charge C ghost equals minus 26. The total central charge is going to be 0. This is going to be essential for the existence of a nilpotent BRC operator. So one of the essential features of the worldsheet theory of critical string is that there has to be a BRC operator that squares to 0, and the stress tensor is BRC exact. That is, in fact, the stress tensor is a BRC transformation of the B ghost. In fact, this can be viewed as a definition of the B ghost, which is essential to everything I'm about to say. And so I want to emphasize that when we speak of the space of string fields, it's not just the space of, I should say that when I say the Hilbert space, I mean the Hilbert space of theory on the circle, or by the state operator map, just the space of local operator at the point. That still holds for the system. But it's essential that I include the states in the space of states of both the free bosons and the ghosts, let's say in the context of the bosonic string. Now the need for including the ghosts, it's a feature, not a bug. Of course, from the point of view of kind of Anshaw string perturbation theory, that's well known. But from the point of view of string field theory, I think I may or may not have the opportunity to give an example on this. But the inclusion of ghosts is absolutely essential. In fact, I think maybe I'll make a few comments about this just in a moment. But in particular, it provides a very nice way to characterize dilettang in the context of nonlinear sigma model, which is kind of always tricky to work with in conformal perturbation theory. Okay, so that's comment number one. Comment number two is that unlike if you learn like string theory from Polchinski or other textbooks, you're used to thinking of the string states, or more precisely asymptotic states, as characterized by a vertex operator or state in this worldsheet theory, but you always impose some extra conditions. The typical conditions you impose are the Siegel gauge condition that says this thing is annihilated by the zero Fourier mode of the B ghost, and the BRT closure. But here, to begin with, I do not impose any such conditions. So there's no BRT constraint. So I do not demand, at least, a priori, that the string field is BRT invariant. That is not an assumption. Now, in the context of, for the closed string field, which is what I'm discussing here by default, although very soon I will move on to the generalization that includes also open strings on the D-instanton, which would lead to open string fields. But at least in the context of closed string fields, there's some additional condition that when I say the space of the states of the worldsheet theory, actually there is a extra condition I have to impose, but it's not something that you would have maybe naively had expected. So this is something that's uncovered by Bartens Wiebach in the early 90s when he first came out with a consistent kind of perturbative framework for the closed string field theory. So it has to be annihilated by B0 minus and L0 minus. So what are these? So L0 minus is defined to be L0 minus L0 tilde, where L0 and L0 tilde are the zeroth Virasoro generator. So this just measures the spin of the operator. It says that as a vertex operator, it has to be spin 0. So that's a constraint. This is a constraint that should be viewed as defining the space of string fields. This is not a gauge condition. And the B0 minus is, the B0 minus is defined analogously. It's the zero mode of the B ghost minus the anti-holomorphic B ghost. So in fact, if you act on this with a BRT operator, you get this spin. So it has to obey this constraint. The reason for this is a bit technical. I won't have time to actually explain, but that's the way it's going to be. In a superstring context, it's going to be GSO projected. It's going to obey GSO projection, so the spin in particular will be integers, and then we restrict to spin 0. And also, in the superstring context, there's going to be a picture number. So in the superstring context, say for type 2 string theory, we're going to have holomorphic, anti-holomorphic NS versus R sector, and there's going to be the so-called picture number that assigns this to be in the -1 picture, and in the NS sector and the -1/2 picture in the R sector. Now, if you have never studied the worldsheet theory of the superstring, these words will mean absolutely nothing to you. But maybe just to say very schematically what it is, I'll just say very schematically that in the case of, let's say, type 2 superstring, including the type 2b case, of course, the type 2 and type 2b differ by the GSO projection, but in the type 2 superstring worldsheet theory, the worldsheet CFT includes 10 free bosons, call them X mu, 10 free fermions, we'll call them psi mu, psi tilde mu for the holomorphic and anti-holomorphic components, or chiral and anti-chiral components, and ghosts, which include the so-called BC and the beta gamma system. So the BC ghosts in the superstring theory are just like the case of the bosonic string theory. The beta gamma system are kind of bosonic ghosts with half-integer spin. You don't have to worry about what it is for the purpose of discussion here. There's kind of a standard technology in treating the beta gamma system by kind of a rebosonization. So we often work with, instead of beta gamma system, the so-called phi xi eta system. So now the notation gets a little confusing. Let me just say briefly what this is. Phi is to be viewed as a chiral, and there's also anti-chiral counterpart, linear dilaton field, and it contributes central charge. It carries central charge. So there's a stress tensor you can write down in terms of phi. It contributes central charge plus 13, and eta and xi. These are operators of weight 0, 0, and 1, 0. They're similar to the BC system, and they contribute to central charge C equals -2. And you can count the central charge 13 minus 2 minus 26 plus 10 plus 5 is actually equal to 0. Okay. And the picture number refers to a particular subspace of all possible kind of vertex you can write down using this linear dilaton field and the eta and xi system. Now I want to get into further details about that due to the obvious lack of time. Okay. In fact, I think I probably won't even really have time to, okay, so I think to save time, maybe I will just say things kind of a bit more qualitatively. This space of string fields is supposed to be interpreted a priori as the space of BV field, or the BV field space, in the sense of the Batalin-Vilkovisky formalism. Now the BV, I think not every physicist is familiar with BV formalism, and I think this is kind of one of the vastly underappreciated thing in mathematical physics. The BV formalism can be viewed as a machine that produces for you a gauge-fixed path integral. Now, you might be familiar with the kind of quantization of gauge theory, where you start with a classical gauge invariant action. You fix the gauge, and you have Fourier pop-up ghosts. You write down the path integral in the gauge-fixed form with the Fourier pop-up ghosts. Now, some class of gauge theories can be described in this way, but not the most general quantum gauge theory. For the most general quantum gauge theory, there's no obvious reason why you should be able to obtain the path integral by starting with a ghost-free, classical gauge invariant action. That need not be the case. Really, you just want to make sure that whatever the gauge-fixed form of path integral is, which with ghosts included, obeys some appropriate consistent condition, that it should be independent of the choice of gauge, and it should be, basically unitarity and so forth. Okay. So the BV formalism is a machine that does that. It has some important application even in the conventional gauge theory, say perturbed Yang-Mills theory. So in fact, if you open Weinberg volume 2, you will see that the discussion of the proof of the perturbative renormalizability of Yang-Mills theory is actually based on the BV formalism. And the reason for that is even though in a UV complete path integral, you might just write some gauge fixed form with Fourier pop-up ghosts, once you start talking about either Wilsonian effective field theory, or once you discuss counter terms, you have to think about a quantum effective action with some, let's say maybe with some UV modes of the matter and the ghost fields integrated out, and you would like to constrain the effective action using gauge invariance. But the question is how to. Once you fix the gauge, so by construction, you're going to lose the gauge invariance. That's the whole point of fixing the gauge. Now, you might say that, once you fix the gauge, the notion of gauge invariance is replaced by BRT invariance. That no longer holds at the level of the effective action. In fact, it's well known that the quantum effective action, say the 1pi effective action, is just explicitly not BRT invariant. The reason for that is very simple. The BRT transformation is nonlinear. There's a difference between the expression value of the product fields and the product expression value of fields. And that difference essentially makes the effective action not BRT invariant. And if it's not BRT invariant, you cannot even use the BRT invariance to constrain the counter terms in your quantum effective action. Now, the appropriate generalization of that is essentially based on the BV formalism. In the case of the Yang-Mills theory, there's a simplified version of that known as the Zinsner-Stein equation that's kind of analog of the so-called BV master equation. But so anyway, what I'm trying to say is that this BV formalism is not something that's alien, that's invented for string field theory. It's something that is ubiquitous for any quantum gauge theory. Okay, but anyway, the point is that the space of all the states in the worksheet CFT Hilbert space with the ghost included is to be interpreted as a BV field space. And in the BV formalism, then we're instructed to say that this space should actually be split into the so-called the space of fields and anti-fields, which are denoted by H plus and H minus respectively. How you do the splitting is essentially up to you. There's a lot of redundancy here. Let me just say that one way to do this splitting in the string field theory context is to grade by the ghost number. Now, in order to formulate the actual path integral in the BV formalism, you have to do some kind of BV gauge fixing. Now, even though kind of morally this is like the usual gauge fixing, but technically it's carried out very differently. The gauge fixing is achieved by picking a
Lagrangian subspace, Lagrangian subspace, I will denote by L, curly L inside H. It's a Lagrangian with back to a symplectic form that's actually Grassmann odd. So there's a lot of kind of a technical recipe that go into this, which I won't have time to define precisely. But all of this can, in the string field theory context, you can look at the very nice review from last year by Sten and Zwiebach. Now, once you have picked the Lagrangian subspace, you're going to say that I'm going to restrict my path integral. Well, I'm going to define the path integral measure of the string field theory to be over that Lagrangian subspace. Maybe I'll go over here. So the string field path integral is going to be schematically of the form integration of the string fields over this Lagrangian subspace of e to the minus some action functional. And this action functional is a action functional in the BV sense. And so the notion of gauge invariance is going to be replaced by the so-called BV master equation. That's going to be some essential consistent condition you're going to impose on this action. Okay, so I think all of this discussion is rather abstract, and time is short. So I think I want to maybe quickly give you a flavor of what the closed string field theory is about before coming to D-instantons. So while a priori this is kind of a quantum formulation, at least to all orders in perturbation theory, let me discuss just the kind of the classical version, just to give some intuition. Well, I have the same space of string fields, but I can write the equation motion. This equation motion can be obtained by varying some action that has to obey some non-trivial consistent condition, as I mentioned, which are the BV master equation. It generally takes the following form. It takes the form QB acting on side. The QB is the BRT operator. It's the same BRT operator that appears there that says the stress energy tensor is BRT exact. Well, this thing plus, let's say, sum over n from 2 to infinity, 1 over n factorial, psi tensor itself n times, bracket. Now, the essential thing is this bracket, this equals 0. Of course, if I don't tell you what the bracket is, this formula is, this expression is extremely general. Of course, it says that to leading order, at linearized level, it says the equation motion will say the string field is QB closed. So that is the analog of the statement, the usual on-shell perturbation theory. We want the vertex operator to be BRT invariant. But in string field theory, that's just the first order. And then there are, correction due to interactions. Now, of course, if I don't tell you anything, a priori, this bracket just means it's some kind of n linear function on the space of string field. Now, I have to tell you something about the property of this bracket. Otherwise, it's kind of trivial. There's no content to the. There's not that much content to this equation. So, in the context of the classical equation motion for string field theory, the essential consistency property, which is actually equivalent to the BV master equation, is that this bracket defines the structure of so-called L-infinity algebra. Now, that sounds very scary, but what it really means in practice is just that for any string field that doesn't necessarily obey the equation motion, if you act on the string bracket, so I'm going to use the shorthand notation psi tensor power n to represent this. If you take the bracket, act on the QB, what do you get? Well, you might say that, oh, I should have some distribution rule, just like a Lie bracket. So I'm not going to keep track of signs and normalization factors. So roughly, you think that, okay, it will be like QB psi with remaining n minus 1 psis. Well, it turns out it's not just that. You need to also have some kind of sum of nested brackets of psi to the m and tensor with psi to the tensor to the n minus m. So if you act on the bracket with QB, you're going to get this distribution rule, but plus contribution with the nested brackets. And they, as you can see, that they have to, as you might imagine, they have to obey some non-trivial consistent condition for that to be compatible with the nilpotency of QB, and this defines the structure of a L infinity algebra. And again, this L infinity algebra is a kind of a feature, not a bug. It allows this equation to have a lot of flexibility. So for example, the notion of gauge invariance will be defined in some natural way with this kind of structure, and the diffeomorphism of a space-time in string field theory will be realized in a kind of in the form of a so-called L infinity gauge transformation, and they have some kind of unusual properties. While you expect that to reduce to the usual diffeomorphism in the weakly curved space-time background, generally the gauge transformations that are analogous to diffeomorphism in string field theory, they do not close under the Lie algebra diffeomorphism. They only close up to homotopy in the roughly speaking. Okay. Another thing I want to mention, just to kind of give a more concrete idea of what we're talking about. Let's say in the bosonic closed case, a typical solution to the string field equation will look like this. You can imagine a perturbative solution look like this. Psi is equal to, in the language of vertex operator, C tilde O plus dot dot dot, where C and C tilde are the holomorphic and anti-holomorphic C ghosts, and these objects have weight -1 and -1. And it is well known that this thing will be BRT closed if O is a weight 1,1 Virasoro primary. So, of course, here, I'm just giving you one example of the kind of thing you might try to write down to solve the equation of motion. Now, what does this mean? What does this represent? Well, whenever you write down this thing, if you see a 1,1 primary, this will remind you of a, this would be a marginal operator in your 2D CFT. So this O will be 1,1 primary in the matter CFT, like the 26 free bosons. So you would expect this to represent a marginal deformation. Now, this marginal deformation may or may not be exactly marginal. Well, in some cases, it will be exactly marginal. So heuristically, this kind of string field, while the dot 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 can represent higher dimension operators, this kind of string field would, if we solve the equation of motion, the physical interpretation of this is that it represents a new space-time background of string theory. So every solution to the equation of motion represents a new, let's say, space-time that is deformed from the old one you started with, say, Minkowskian. Heuristically, you would like to think that a string field solution like this would be physically equivalent to deforming the worldsheet CFT by this marginal operator. And that to leading order is correct. But the precise relation beyond leading order is very complicated. Now, the point is that if you want to deform the worldsheet CFT, starting with a marginal primary, you can do conformal perturbation theory, whatnot, and of course quickly things become very complicated. Well, in string field theory, you never deform the worldsheet theory. So we're going to always keep the same worldsheet CFT. But nonetheless, we're going to be able to access all different spacetimes just by turning on different string fields that solve the equation of motion. And all the complication with conformal perturbation theory gets repackaged into these string brackets. So this string brackets capture everything to all of the conformal perturbation theory in some very inexplicit way. So if you try to compute the correction of this, plus da da da, you will be able to understand whether the solution, for example, exists, whether this deformed worldsheet theory somehow exists or not, just by solving the string field equation. So basically, you don't have to think about so all the issues about scheme dependence will be encoded in how you construct these string brackets, and there will be some ambiguities, but it was understood systematically that the different choices of string brackets are always related by field redefinition. So in that sense, there's one underlying string field theory, despite the huge amount of redundancy in the formalism. Okay, so I really have to move to D-instantons. In fact, otherwise I'll barely have time to state even the conclusion. So let me say a few words about D-instantons. It's very difficult to erase. Okay, so there are many applications of string field theory which I won't have the time to discuss here. I'm just going to now focus on its application to D-instantons. So the D-instantons, as a boundary condition of the worldsheet, it was already kind of noted by Polchinski the year before he discovered the true row of D-branes. So, so Polchinski, back in '94, understood that you can have non-perturbative effects characterized by D-instantons. What does it look like? Now, suppose you consider full graviton scattering amplitude, our favorite object, let's say in type 2B string theory in 10 dimensions. We have a genus expansion. We have the tree level that gives you Virasoro-Shapiro amplitude. You all know that. There's a one loop, there's two loop, and so on and so forth. Now, this perturbative expansion may or may not converge. We know that actually, at least to low derivative ordinary derivative expansion, it converges. In fact, not only it converges, it truncates, but not in general. Now, the idea is that there are going to be some non-perturbative contributions. These non-perturbative contributions sometimes are unambiguously defined, sometimes are not. And they look like the following. So heuristically, they look like e to the, let's say, diagrams with worldsheet diagrams with boundary. So here's this is meant to be a disk. This is meant to be an annulus, and so on and so forth. But here, these diagrams don't have any vertex operator, closed string vertex operator insertion. You also need to have closed string insertion. So then you can have things like 4 disks. So this is one term, and then there are many other. Maybe let me write like this. So what am I talking about here? Okay, so in the simplest case of just single d-1 brane, you should think of which is represents one contribution out of many in this sum, to the extent you can define how to sum it up. All the boundaries here of the worldsheet are subject to the same boundary condition. So if you have multiple d-instantons, you take the direct sum of the boundary condition. In the case of a single d-1, it's just a single boundary condition, and you take all the boundaries to be subject to the same boundary condition. So because the boundaries are correlated, even though this diagram looks disconnected, it contributes to a connected amplitude. So in particular, here you have a closed string vertex operator inserted here, 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 here. On each disk, the spacetime momentum is not conserved because spacetime momentum conservation is broken by the d-instant boundary condition. But that conservation law gets restored at the end. Now, in the kind of naive on-shell approach to this, you would just say that we're going to integrate this diagram over the modular space.
Sorry, just naive question. Why don't I have a disk with 4 points inside?
That's at the third order. So, because of the Euler characteristic gets, this is the one with the highest Euler characteristic. So, at the next order, for example, you have disk with 2, and 2 disks each with 1, and there's other topology. So at some point you get a disconnected one, and then of course you can have things that are more complicated. You can have additional like handle attached to this and so forth. Right. Okay. Well, I mean this second one is already very complicated actually. This one so far we don't usually need to deal with it. That occurs. So this is organized. So usually we refer to this structure as the D-instanton perturbation theory. That is, it's like expanding around a new saddle. But the unusual thing about this compared to the usual gauge theory is that this expansion is controlled by a different coupling expansion than that. Namely, this one, the first expansion is controlled by the closed string coupling. This second is controlled by open string coupling. So they have they come in different powers. Now, if you imitate what you normally do in a gauge theory, you will say that, okay, you have an instant background, you calculate this amplitude mediated by the instanton, you have the integrator of the moduli space. Morally, you would like to do that in string theory as well, and that's how it was done before Ashok-Sen work in 2020. So before that, we thought that we're supposed to integrate over the moduli space, but the problem there is that we do not have a priori way to fix the measure. Of course, you can fix it by symmetry in the case of, you can constrain it by symmetry. So in case of single d-1, is translation invariant. There's also supersymmetry, you can use that. So they're both bosonic and fermionic collective modes. But even in that case, you cannot fix the normalization. So the main insight, one of the major insights of Ashok-Sen is that actually, you don't need to think about this integral of a moduli space. It's already encoded in this annulus diagram. So more precisely, this annulus diagram, you can think of it naively is some kind of determinant you get by integrating out the open string degrees of freedom. But open string fields actually include the moduli. So the infinitesimal moduli deformation are part of the open string degrees of freedom. So by carefully interpreting what this annulus diagram actually means, you would actually restore the moduli integration. So much of the subtlety has to do with interpreting what this annulus diagram actually is, because naively it's just divergent, and it's ill-defined. And sort of the major kind of contribution of Ashok-Sen is to replace this naive prescription with something that's completely well-defined within the context of open plus closed string field theory. That is the string field theory of closed string in the bulk plus open string on the D-instanton. Now, that's the story for the closed string amplitude. Let me just say maybe briefly what is the output, what are some examples of the output of this. So I think a lot of you know that the space-time effective action of type 2B string theory, the massive effective action contains some R to the fourth effective coupling. I'm not going to write a tensor structure like T8 contracted with R to the fourth. There's a coefficient that depends on tau and tau bar. All right. Now, it was understood in this case that it's actually BPS protected, which in particular implies that f of tau and tau bar obey some differential equation. And if you combine that differential equation together with S duality, together with the boundary condition, which is fixed by tree level result, like in the expanding Versor-Shapiro, as Fernando had talked about, then you can pin down this function completely. And if you look at what the function is, so this was pinned down by Green and Gutpearl in their seminal paper from 1997, I think. If you look at explicitly what this function is, it looks like the following. There's 2 zeta 3 tau to the power 3 halves. So that's the zeta 3 that Fernando likes. And then you have 2 pi squared over 3 tau 2 to the minus 1/2. So the first term is a tree level contribution. The second term is one loop contribution. And then it's perturbative one loop exact. So in perturbation theory, that's it. There's no 2 loop contribution or higher. And then you have some 4 pi sum n greater than or equal to 1 e to the 2 pi I n tau plus e to the minus 2 pi I n tau bar times some numbers, square root n, sigma n, 1 plus order tau 2 inverse. I'm not going to write all the terms. You can write them down if you want. They correspond to these higher topologies. So the sigma n here is sum over divisors of n, integer n, positive integer n, 1 over divisor squared. This famously is known to be the answer of the IKKT matrix integral. So that is not an accident. There's a reason that IKKT matrix integral show up, but you don't need to know any of that. Just based on supersymmetry and S duality invariance, you can pin down this answer. The thing I want to point out here, of course, is that all of these are instanton contributions. They have to be there for S duality to hold. So they have to come from the D-instanton calculus. And also in this case, regardless of whether the perturbation theory truncates or not, some of the instant contributions are unambiguously defined. I guess my time's up, but I'll just stay. I'll need a few minutes to say the answer if that's okay. The so-called charged instantons will give a contribution that is not invariant under the shift of tau 1. You see, perturbation theory only depends on tau 2 because tau 2 is the, like I say, is the inverse string coupling. But the tau 1 is the Raman-Around axion. And the string perturbation theory, at least in the closing sector, is completely blind to the value of the background R axion. But that is not the case for the instant contribution. So instant knows about tau 1 dependence. And that's completely unambiguous. And without that, S-duality would not be possible. OK, so I'm not going to even draw the topological diagram that would contribute to this D-1 effect on the D3 brane. I'll just state the results. So in the case of the D3 brane, we can discuss the analogous Ward volume effective theory. There's some effective theory, which as I mentioned, was the dBi plus corrections that includes schematically d4th f to the 4th term, plus . And this coefficient has a tau and tau bar dependence. Let's call this, use different notation. So the question is, what is this function here? So this is the kind of this is also the first term in the derivative expansion that has non-trivial D-instanton contribution. Now, Green and Gutperl back in the days made a conjecture about this. So Green and Gutperl conjectured that this f of tau and tau bar up to some normalization coefficients, which I will not bother to write, is log of tau 2 eta tau to the 4th. Now, as far as I can tell, they conjectured this because they know that this agrees with the tree level and the one loop answer, and the function that looks nice. You know, and it's S-duality invariant. But unlike this R to the 4th coefficient, it is not at all constrained by any differential equation because this is an unprotected term. If you look at the instant expansion, you'll find the instant expansion. So this expansion looks like this plus log tau 2. It starts minus pi over 3 tau 2. That's the tree level. This log of tau 2 is quote unquote one loop. This has to do with the scheme dependence that you know that I mentioned earlier. And then there's some instant expansion, sum over n greater than or equal to 1, 1 over, sum over divisors of n, 1 over divisor rather than 1 over divisor squared, e to the 2 pi I n tau, plus e to the minus 2 pi I n tau bar. Now, this conjecture by Green and Gutperl would also imply that this two-loop vanishing at two-loop and three-loop and so on and so forth. That's a pretty strong statement for a non-BPS protected term, and which seems to be hard to believe. But now we have the technology to calculate the instant contribution from first principle in string field theory using the same formalism as Ashok sense. We calculated the little n equals 1, which is the one D-instant contribution at the leading order in this D-instant perturbation theory. Most of the work is about pinning down the factors of 2s and pi's. And after a lot of work, which it will take another hour to explain, which I'm obviously not explaining, we found the coefficient to exactly agree with the conjecture of Green and Gutperl. So that was actually kind of shocking to us, which make me now tend to believe that this conjecture might actually be correct. Now, at the moment, we're trying to work on the generalization of this to the higher instant number, which we can also do, and we have reduced the computation down to a matrix model. But this matrix model has to be calculated using some localization because direct numerics is too hard unless you do Monte Carlo, and we're not Monte Carlo professionals. So we're trying to pin it down with localization. But as far as I know, in the literature, while this matrix model has been studied using localization, we cannot trust their factors of 2s and pi's. And for us, that's very important. So right now, we're trying to pin down that and try to see whether the higher coefficients also agree or not. So far, still off by some factor of n squares, but maybe that will get resolved. So we're not sure yet whether higher order contributions will confirm the Green-Gutperl conjecture or not. If it does, which I think is actually potentially likely, then it would imply that there's some underlying principle that constrains this non-BPS protected term that we have no clue about. And I'll just stop here.
Yeah, Shai.
That appears with r squared f squared.
R squared f squared.
Yes. So the r squared f squared coefficient, which is protected, its coefficient is the exact same function you're finding. I'm wondering if that's related somehow.
I don't have anything terribly useful to say about that. Of course, when it's protected, yeah, you know, you have a rigorous argument. But I should mention here that, you know, it's possible to also check whether the two-loop result is vanishing or not. As far as I know, nobody has done this. I think the technology exists. You just have to modify the Docker and the phone close-string two-loop computation a little bit and carefully analyze like its duration expansion. You know, maybe you know someone that's not us will do it. If you work hard enough, you can figure out and just check whether the two-loop vanishing result is actually true or not. But yeah.
Murat, can someone pass the mic over in that direction, please? Thank you.
Hi. So you drew this analysis diagram of the other things. How can I see the number of D-instantons in this expansion?
Did you say non-BPS?
No, the number of D-instantons.
Oh, the number of D-instantons. That will be characterized by the boundary condition. So, for example, if I have n D-instantons at separate points, then I just have the boundary state. Well, the boundary state will be just the sum of the one for each of these instantons. Now, the nice thing about the open string field theory is that you don't have to make a choice because all of these are related by turning on open string field. So you just need to choose one particular background, you know, you can start with the n D-instanton, and you know, perturbatively you can access all the possible configurations by integrating over open string fields. That's essentially how the IKT matrix model showed up here, at least in the way that Ashok reproduced this from the instant calculus. So the integration of open string fields would reduce in the leading order to this IKT matrix integral.
Any other questions for Shi? If not, let's thank Shi for a beautiful talk. And don't. So now we will have a short address, formal closing address by Leonardo, a surprise address. Maybe just before I pass it over to Leonardo, you were all at the dinner, or 99% of you were at the dinner, so I will not repeat what I said over the dinner, except I would like to, again, once more, thank the staff at both ICTP and Principia, and in particular as representatives of ICTP and Principia, Tiago and Laura that were there every day, making sure the right screen is showing and following the blackboard diligently. So please, a big round of applause to them. And I'll pass it over to Leonardo, and maybe just on behalf of all the PIs of the collaboration, I think we should thank Leonardo for being an amazing boss over this few years.
Well, thank you all.
I think, yeah, Leonardo and Slavo were a great team of bad cop, good cop. I mean, no one knows which one is which. And yeah, it was a real privilege. So there are many Simon's collaborations, and with different characteristics, and ours is characterized by being the best. And that's to a great extent because normally people that want to be heads of collaborations and to be involved in politics are not the people who want being heads of collaborations and in charge of politics. And Leonardo and Slava, I thought, were really notable exceptions, super pragmatic, always replying super fast to emails, engaged in science, and extremely open to everyone. And so that was a great luck that we had to be part of this collaboration over these past few years. So thank you.
Thank you, Pedro. So yes, so first I want to also thank my co-organizers for this meeting, and in particular the local people who did all the work, Connor, Andrea, who's an honorary local person, Pedro, Nathan, of course, thank you very much for your hospitality over the years, and this year in particular, all the staff. It's been really great. But then, apart from this local thanks, I think it's the final meeting under the formal umbrella of the Simons collaboration, but as I will announce at the end, this is absolutely not the end. It's only the end of the beginning. So I think it's time to take stock. It's in fact the 14th annual meeting since the 15th, maybe. The 15th annual meeting since our humble beginnings in 2011 in this truly incredible first gathering that we had at the Perimeter Institute, which we named Back to the Bootstrap. And so I had to remind myself a little bit of the history. I went back to old emails, I looked at web pages. So it all started, I will take credit for this, when in Copenhagen, Pedro and I were giving some lectures, and there was a vague circle of ideas that we thought was kind of emerging. There was this curious 2008 paper by Rattazzi, Richkov, Tonni, and Vicky. I look at the paper. By the time we met the first time in Perimeter, it had maybe 30 citations. It wasn't really widely noted, but it clearly seemed important. And in fact, the third citation of the paper that I just looked up was from Hellerman. So Hellerman very presciently realized that the same circle of ideas could be used for the modular bootstrap. And the seventh citation is this paper, famous paper by the HPPS paper by João Jopolshinsky and collaborators that had this vision about how holographic theories emerge from conformal field theory, and they felt that perhaps the bootstrap is one way to go. So Pedro and I thought that there was some, also there was this curious, extremely technical, hardcore papers by Dollar and Osborne that clearly felt important, and so we invited them to our first meeting, and it was a very exciting time. It was a bit unclear what to do, but people were brimming with ideas. It was an incredibly informal atmosphere, and over the next few years, with this series of Back to the Bootstrap meeting, a vision emerged and solidified. And it's a vision which is still with us. So I will not be able to really do justice to this vision, but what is the general vision? The vision is that there's theory space, so you should lift your gaze from trying to solve a concrete model and look at the space of theories. It's a theory that in this modern incarnation is probably due to Wilson, but it's even more general than when Wilson thought. And then you want to carve out theory space using consistency principles. So the idea that consistency principles are important, of course, goes back to the old version of the S-matrix bootstrap in the 1960s, but I think the idea of theory space is more modern. And so in particular, the idea that you should retreat a bit, should be a little bit more modest. You shouldn't necessarily to try to solve the theory of everything or to solve the theory of certain directions from first principles, but you should, if you can just carve out theory space and make a plot that is shrinking, that's good enough. And that was clearly the original insight. That was a proof of principle in the 2008 paper, which has been, I would say, enormously influential, obviously for the conformal bootstrap. But I think more generally, for example, to just do a personal modest example, my own work on protected algebras in supersymmetry, although it's technically completely unrelated to the numerical bootstrap, it's the same idea. There's a space of theories, there's consistency conditions, you should try to axiomatize them and then look for solutions. And so, so that's the vision that we articulated, I think, in our original proposal. I went back to the original proposal, as honestly, it's sheer prophecy. So everything we said we would do, we did, and a lot more. So what I think has characterized the collaboration over the years is first the science, and what's great about this community is that there is, at the same time, conceptual unity is this principle I just mentioned, the idea that you carve out theory space using consistency principle, but then also great diversity of techniques and ideas. And again, I'm not going to be able to really do justice of everything we do, but well, you start by focusing on conformal field theories, which are these signposts in the space of theories, and that's of course the arena of the conformal bootstrap, especially the numerical conformal bootstrap, which has exceeded, I don't think anybody could have foreseen back then the heights of sophistications that this enterprise has reached. In the opening talk of the conference, we saw that this has become truly its own subfield of theoretical physics, incredible precision, incredible reach. But then, of course, conformal field theories are just these special points in theory space. You want to connect them by RG flows, and that's how you do that. Well, by using abstract data, you can perhaps try a Hamiltonian truncation. Or, well, actually, since the conformal bootstrap was so successful, this inspired some of our colleagues here to say, well, perhaps we should revisit the asymmetric bootstrap, but again, in this more modern view that we aren't trying to find the final asymmetrics of the world. We write down like Veneziano thought, we write down the answer for QCD. Well, let's carve out. And so I don't think also in our original proposal, we mentioned some vague ideas about the asymmetric bootstrap, but this to me actually has been perhaps the main surprise of how successful that has been. And I insisted that at the beginning that a few moments ago that the numerical bootstrap has become incredibly sophisticated, and that is still one of our main areas. But I think the real surprise to me is that we started mostly Euclidean, and over the years we have become more and more Lorentzian with the S matrix, with Lie raise operators. Ian gave us a beautiful set of lectures about applications, even to QCD, and actually also to quantum gravity. So yes, so if you are in a gap phase, or if you're moving using conformal field theories, you can, for example, study the S matrix. You can look at supersymmetric subtensors, which are special properties which are protected, and then maybe using these protected quantities, you can fit them in the numerical bootstrap. And so this is both in these general conceptual ideas and in this concrete connection. One of the ways in which what we do is both a unifying theme, but also has many diverse facets. So what I find most remarkable all of this, and it's really what the 2008 paper made clear, is that you start with this general enunciation of this philosophical principle that not anything goes, and you should be able to determine these isolated points in theory space. I say, well, that sounds nice, but what are you going to do with it? And what actually we have shown is that far from being just some lofty abstract philosophical idea, this is extremely concrete, completely rigorous, and surprisingly effective. And so I think we still need to understand, the unreasonable effectiveness of the bootstrap. Why is it that we got so lucky, and why is it that we can go so far with this apparently vague philosophical enunciation? And then, of course, there's quantum gravity. I don't think, unfortunately, we have quite solved that yet. We are well on our way to solving quantum field theory, but quantum gravity still remains elusive, and indeed, this is part of the original motivation. What is really that's making quantum field theory holographic? Well, yes, you can enunciate certain criteria, and that was one of the achievements of the original paper by HPPPS, but I think we still don't quite understand. If I write down, as Joao was emphasizing in his talk, if I write down a matrix model, Lagrangian, is this going to have emergent gravity or not, is something we still don't understand. Although we have made a lot of progress, and the progress is, of course, one of the main connections is through the SCFT, quantum field theory and ADS. Quantum field theory and ADS connects, there's another of the bridges that I forgot to mention earlier. Quantum field theory and ADS connects the conformal bootstrap with the asymmetric bootstrap in a truly beautiful way. And so all in all, we have this powerful web of connections. That is what I think makes our meeting so exciting, because each of us is working on an area, but it's very easy to find a connection because of the conceptual unity of what we do. Apart from progress in each of these areas, which I think is very tangible, I was really happy in all the talks of this meeting. This general circular ideas continues to be an inspiration. We saw John McGreevy's lectures on the entanglement bootstrap. Who would have thought that you could bootstrap entanglement, but actually you can. We saw these lectures on quantum mechanics bootstrap, which is sort of a different flavor, but still within the spirit of using consistency conditions to get concrete results. So, kudos to all of you. I think collectively over the years, you have changed the landscape of theoretical physics. I don't think this is an exaggeration. There's no Monte Carlo talk which is complete without mentioning some bootstrap results. There's no PhD school which is complete without a significant representation from bootstrap ideas, or ditto for the annual strings conference. And so this has been a paradigm shift, I think, in theoretical physics, which has been made possible by all of you. And I think since the very beginning, it has been clear that this is a very special community. Since the very beginning, we have insisted in having informal interactions, Blackboard talks. There's a bit of a safe space, which I think is clear to any visitors that come casually to our meetings. Oh, you're special, because you can ask tough questions, but it's clear that you're not asking the question to show off, but because you're really interested in the answer. Our meetings are really a lot more interactive than any other meeting I've seen from other collaborations or more generally. And so the community is here, and it's here to stay. We have mentored over the years truly a couple of generations of postdocs and students. Thank you for coming, and this is not the end. So the Bootstrap series of meetings will continue. That's what I was going to announce. Stay tuned. We don't know exactly when or where, but it will happen. It will continue to happen because this community needs to prosper. And what can I say? We have a Slack channel. It will continue for the time being. If it's going to be discontinued, we will certainly find some other platform for all of us to continue interacting. And so thank you. So being the director of this collaboration has truly been one of the great honors of my professional career. Thank you to all the PIs, to all the postdocs, to all the students. And this is to be continued. Thank you.
Very good. Now we can go for lunch and use up all the vouchers.